Right now, you are spinning on a tilted rocket over 1,000 miles per hour, and that tilt is the only reason you're alive. Remove it, and Earth becomes a frozen wasteland at the poles and a burning hellscape at the equator. No seasons. No stable climate. No you. But here's what nobody tells you. Earth doesn't just spin. It rotates on an angle, exactly like a rotisserie chicken turning slowly over a cosmic flame. The sun is the heat source. Our planet is the meat. And that 23.5-degree tilt. It's the spit. This isn't a metaphor. It's physics. Dr. Sara Seager, MIT astrophysicist and planetary scientist, uses this exact comparison when explaining why Earth remains habitable. She calls our axial tilt the unsung hero of habitability, a geometric accident that distributes solar energy across our entire planet instead of concentrating it in bands of extreme heat and cold. Think about what's at stake here. Without this precise angle, life as we know it could never have evolved. The temperature gradients that drive our weather, our ocean currents, our entire biosphere, all of it depends on Earth cooking evenly on its celestial rotisserie. By the end of this journey, you'll understand exactly why our planet's tilt exists, what maintains it, and the terrifying truth about what would happen if it changed. But first, you need to see the mechanism. Imagine looking down at Earth from above the North Pole. You'd see our planet rotating counterclockwise, completing one full turn every 24 hours. Simple enough. But now shift your perspective. Look at Earth from the side, from the plane of its orbit around the Sun. This is where it gets interesting. Earth doesn't spin perfectly upright. Its axis, the invisible line running from pole to pole, leans at an angle of 23.5 degrees relative to its orbital plane. This angle is called axial obliquity, and it's been measured with extraordinary precision by NASA's Deep Space Network and the European Space Agency's tracking systems. Here's why this matters to your existence. As Earth orbits the Sun over 365 days, the tilted axis always points in the same direction, toward Polaris, the North Star. This means that for half the year, the northern hemisphere tilts toward the Sun, receiving more direct light. For the other half, it tilts away. Seasons. The fundamental rhythm of life on Earth. All because our planet is crooked. Dr. David Stevenson, planetary scientist at Caltech, has spent decades studying how Earth acquired this peculiar angle. The leading theory points to a cataclysmic collision 4.5 billion years ago, a Mars-sized object called Theia slamming into the young Earth with enough force to knock our planet sideways and splash debris into orbit. That debris became the Moon, and the Moon, as you're about to discover, does something even more remarkable than create tides. It acts as a stabilizer, a gravitational anchor that prevents Earth's tilt from wobbling chaotically over millions of years. Without it, our rotisserie would spin out of control. But there's something that changes everything about how we understood this process, something discovered only in the last decade that rewrote the textbooks on planetary habitability. For centuries, we had no idea Earth was tilted at all. Ancient astronomers knew the seasons changed. They tracked the sun's path across the sky, watched it climb higher in summer and sink lower in winter. But the mechanism behind this cosmic dance remained invisible, hidden in plain sight. It took until the 16th century for Nicholas Copernicus to place the sun at the center of our solar system. And it took another 200 years before scientists understood that Earth's axial tilt, not its distance from the Sun, created the seasons. Here's the part they got wrong. They assumed the tilt was permanent, fixed, unchanging. They couldn't have been more mistaken. In 1920, Serbian mathematician Milutin Milanković published a radical theory. He proposed that Earth's tilt wasn't constant at all, it oscillated slowly over tens of thousands of years, shifting between 22.1 and 24.5 degrees. These wobbles, combined with changes in Earth's orbital shape, triggered ice ages. The scientific community dismissed him. His calculations were too abstract, his predictions untestable with 1920s technology. Milanković died in 1958, never knowing he was right. Decades later, deep-sea sediment cores confirmed his cycles with stunning precision. Dr. James Hayes of Columbia University, alongside Nicholas Shackleton and John Embry, published the landmark 1976 paper that vindicated Milanković. The evidence was locked in ancient ocean sediments, a chemical record of ice ages perfectly matching the Serbian mathematician's predictions. But this discovery opened a terrifying door. If Earth's tilt could change by 2 degrees over 41,000 years, what stopped it from changing more? What kept our rotisserie from tilting wildly, say, 90 degrees, like Uranus, which essentially rolls around the Sun on its side? The answer came from an unlikely source. The same catastrophic collision that created the Moon. In 1975, planetary scientists William Hartmann and Donald Davis proposed the giant impact hypothesis. They argued that a Mars-sized protoplanet, later named Theia, slammed into early Earth at a glancing angle. The collision was so violent it liquefied both worlds, splashing molten debris into orbit. That debris coalesced into the Moon within a century. An eye blink in cosmic time, Apollo lunar samples provided the smoking gun. When scientists analyzed Moon rocks brought back by astronauts, they discovered something astonishing. The oxygen isotope ratios in lunar samples were virtually identical to Earth's, a chemical fingerprint proving the Moon formed from our planet's own mantle, mixed with the impactor. Dr. Robin Canup at the Southwest Research Institute has run hundreds of computer simulations of this collision. Her models show that Theia struck Earth at roughly 4 kilometers per second, at an angle between 45 and 60 degrees. The impact tilted Earth's axis, and created the stabilizing companion we now call the Moon. Here's where the first major complication emerges. In 1993, French astronomer Jacques Lascar at the Paris Observatory ran the most sophisticated orbital simulations ever attempted. He wanted to answer a simple question: what would happen to Earth's tilt without the Moon? The results were catastrophic. Without lunar gravitational influence, Earth's axial tilt would swing chaotically between 0 and 85 degrees over just a few million years. The planet would tumble. Poles would face the Sun directly. Equators would freeze. Climate zones would shift so rapidly that complex life could never adapt. Lascar's team called it rotational chaos. The Moon, it turned out, wasn't just a companion. It was a gyroscopic anchor, a gravitational weight that dampened Earth's wobbles and kept our rotisserie spinning at a survivable angle, but no one expected what came next. For decades, we assumed other Earths would spin like ours, tilted at a comfortable angle, stabilized by a large Moon. Seasons cycling predictably across continents. It seemed logical, almost inevitable. Then we started finding exoplanets. And everything we thought we knew was wrong. In 1995, Michel Mayor and Didier Queloz at the Geneva Observatory detected the first planet orbiting a Sun-like star. 51 Pegasi b was a monster, a Jupiter-sized world whipping around its star every 4 days, so close its atmosphere seared at over 1,000 degrees. This was not the Earth-like world anyone expected. Within a decade, NASA's Kepler Space Telescope cataloged thousands more. Rocky worlds. Gas giants. Planets orbiting binary stars. The galaxy, it turned out, was teeming with planets, but almost none of them resembled Earth. Dr. Sara Seager at MIT began asking a disturbing question. We could measure exoplanet sizes, masses, orbits, even atmospheric compositions. But what about their tilts? What about their rotisserie angles? The answer was humbling. We had almost no idea. Measuring axial obliquity from light-years away pushes technology to its absolute limits. Unlike mass or radius, tilt doesn't leave obvious signatures in transit data. For most exoplanets, we're flying blind. But in 2018, a breakthrough. Dr. Sarah Milholland at Yale, working with Gregory Laughlin, published a groundbreaking analysis of compact planetary systems discovered by Kepler. Using gravitational interactions between neighboring planets, they inferred obliquities indirectly. The results stunned the scientific community. Many exoplanets showed signs of extreme tilts, worlds spinning nearly sideways, or tumbling chaotically with no stable orientation. Some systems appeared locked into resonances that could flip planetary axes over million-year timescales. Earth's gentle 23.5 degrees suddenly looked like a cosmic miracle. Dr. René Heller at the Max Planck Institute for Solar System Research has modeled what life would face on these tilted worlds. Imagine a planet inclined at 60 degrees. Its poles would experience months of continuous sunlight followed by months of total darkness. Temperatures would swing by hundreds of degrees. Ice caps would form, melt, and reform in geological eye blinks. Heller calls these tilt-driven climate catastrophes. Any life attempting to evolve would face constant extinction-level stress. But here's where the scientific community divides. Some researchers argue Earth's stability is extraordinarily rare, a 1 in a million configuration requiring precisely the right collision, precisely the right moon, precisely the right orbital dynamics. This is the rare Earth hypothesis, championed by paleontologist Peter Ward and astronomer Donald Brownlee. Their argument is sobering. Complex life might be vanishingly uncommon because stable rotisseries almost never form. Others push back hard. Dr. Jack Lissauer at NASA Ames Research Center points to simulations showing that many planetary systems could achieve stable obliquities through different mechanisms. Massive planets in outer orbits can dampen tilt oscillations. Thick atmospheres can buffer temperature extremes. Moons aren't the only solution. The debate remains unresolved. But one discovery shifted the entire conversation. In 2021, researchers using data from the TESS mission identified a rocky exoplanet in the habitable zone of a nearby red dwarf. Models suggested it might possess a substantial moon, the first potential Earth-Moon analog ever detected beyond our solar system. If confirmed, it would prove our rotisserie configuration isn't unique. That somewhere in the galaxy, another world might be spinning at just the right angle, cooking evenly under alien starlight. But confirmation requires technology we don't yet have, and so the question hangs suspended in the darkness between stars. Is Earth's tilt a cosmic fluke, or the first example of a universal recipe for life? The answer may redefine our place in the universe. The breakthrough came from an unexpected direction. Scientists weren't looking at tilt. They were looking at atmospheres. And what they found changed everything about how we understand planetary habitability. In 2022, the James Webb Space Telescope turned its golden mirrors toward TRAPPIST-1, a red dwarf star 40 light-years away, orbited by 7 rocky planets. 3 of them sit in the habitable zone. For years, astronomers had speculated about their potential for life. JWST delivered the first verdict. And it was devastating. Dr. Bjorn Bennick at the University of Montreal led the atmospheric analysis of TRAPPIST-1b, the innermost planet. The data showed no substantial atmosphere. Solar radiation had stripped it bare. Without an atmospheric blanket, surface temperatures swing hundreds of degrees between day and night. But here's what made scientists pause. TRAPPIST-1b is tidally locked, one face eternally baking, the other frozen in permanent darkness. No rotation. No tilt. No rotisserie effect at all. The planet never had a chance. Dr. Victoria Meadows, director of NASA's Virtual Planetary Laboratory, connected the dots in a landmark 2023 synthesis paper. She and her team modeled the interplay between axial tilt, atmospheric circulation, and surface temperature across hundreds of simulated planets. The conclusion was profound. Planets with moderate tilts, between 15 and 35 degrees, showed dramatically better heat distribution than their tidally locked or low-tilt counterparts. The rotisserie effect, it turned out, wasn't just helpful. It was essential for maintaining liquid water across large surface areas over billions of years. Meadows called it obliquity-enhanced habitability. Earth sits almost perfectly in the sweet spot, but the revelation went deeper. Dr. Rory Barnes at the University of Washington has spent a decade building the most comprehensive habitability models ever constructed. His VPLanet software simulates planetary evolution across billions of years, tracking tilt, orbit, atmospheric loss, volcanic outgassing, and dozens of other variables simultaneously. His team discovered something remarkable. The Moon doesn't just stabilize Earth's current tilt. It locked our planet into a configuration that maximizes long-term climate stability. Without lunar influence, Earth would have oscillated through the habitable tilt range chaotically, sometimes favorable, sometimes catastrophic, never consistent. Life needs consistency. Evolution requires stable conditions across millions of generations. Random tilting would reset the biological clock over and over, preventing complex organisms from ever emerging. The Moon gave Earth something priceless. Time. 4 billion years of relatively stable climate. Enough time for single cells to become trilobites, dinosaurs, primates, Every species that ever lived owes its existence to a collision that happened before Earth had oceans. This synthesis reframes the search for extraterrestrial life entirely. Dr. Lisa Kaltenegger, director of the Carl Sagan Institute at Cornell, now argues that future missions must prioritize exoplanet obliquity detection. Knowing a world sits in the habitable zone isn't enough. We need to know if it's spinning correctly. NASA's proposed LUVOIR and HABEX space telescope concepts include instruments designed to detect seasonal variations on exoplanets, indirect signatures of axial tilt. The European Space Agency's Plato mission, launching in 2026, will measure stellar wobbles with enough precision to infer planetary rotation states. For the first time in history, we're building tools to find other rotisseries, but open questions remain. Can planets achieve stable tilts without large moons? Do super-Earths with stronger gravity resist chaotic tumbling? Could life adapt to extreme obliquity cycles we consider hostile? The data doesn't exist yet. We're still gathering ingredients for an answer that may take generations to complete, but the real question isn't what we found. It's what it means. You are alive because of geometry, not intelligence. Not luck. Not divine intervention. Geometry. A 23.5-degree angle, maintained for 4 billion years by a moon born from catastrophe. This single fact carries implications that stretch far beyond Earth. Dr. Natalie Batalha, former Kepler mission scientist and now professor at UC Santa Cruz, frames it starkly. We spent decades searching for planets in habitable zones, the right distance from their stars for liquid water. But distance was never enough. Temperature is only half the equation. The other half is distribution. A planet can sit perfectly in the habitable zone and still be uninhabitable if its heat concentrates in the wrong places. Tidally locked worlds bake on one side and freeze on the other. Zero-tilt planets trap heat at the equator while poles become permanent ice caps. Chaotically tumbling worlds never stabilize long enough for life to gain a foothold. Earth's rotisserie solves all of these problems simultaneously. Future missions will hunt for this configuration. NASA's Nancy Grace Roman Space Telescope, launching in 2027, will image exoplanets directly for the first time, capturing light reflected from alien surfaces. Seasonal brightness variations could reveal axial tilts across interstellar distances. Dr. Aki Roberge at NASA Goddard is already preparing detection protocols. Her team calculates that a planet tilted like Earth, orbiting a Sun-like star within 50 light-years, would show measurable seasonal signatures. We could identify another rotisserie within our lifetimes. But finding one won't just answer scientific questions. It will answer existential ones. For centuries, humanity wondered whether we were alone. Now we understand the question was incomplete. The real question is whether the conditions that created us can exist elsewhere, whether the cosmic recipe has been followed in other kitchens, under other suns. Every exoplanet with stable tilt becomes a candidate. Every moon-forming collision becomes a potential genesis, and here, we return to where we began. You are spinning right now. 1,000 miles per hour at the equator. Tilted at 23.5 degrees toward Polaris. Rotating through sunlight and shadow, summer and winter, exactly like a rotisserie chicken turning slowly over a flame. This image, playful as it sounds, contains a profound truth: the universe is not gentle. It is violent, chaotic, and overwhelmingly hostile to life. Planets tumble. Atmospheres strip away. Stars flare. Collisions shatter worlds into debris. Against this backdrop of cosmic destruction, Earth maintains its angle, century after century, millennium after millennium, epoch after epoch. The moon holds us steady. The sun provides the heat. And life flourishes in the narrow band of stability between chaos and sterility. Carl Sagan understood this better than anyone. In 1994, reflecting on the pale blue dot image captured by Voyager 1, he wrote words that still resonate across decades. The Earth is the only world known so far to harbor life. There is nowhere else, at least in the near future, to which our species could migrate. Like it or not, for the moment the Earth is where we make our stand. He could not have known how literal that statement would become. We now understand that our stand depends on an angle. A tilt. A geometric accident frozen in place by an ancient collision. You exist because 4.5 billion years ago, something went catastrophically wrong, and turned out catastrophically right. The rotisserie keeps turning. The seasons keep cycling. And somewhere out there, perhaps around a star we haven't yet named, another tilted world may be cooking its own recipe for life. The universe is still calling. Will you answer? Close your eyes for a moment, feel the ground beneath you. Solid. Stable. Predictable. You trust it without thinking, the way you trust your own heartbeat. But that ground is spinning. Tilted. Hurtling through space at 67,000 miles per hour around a nuclear furnace. And the only reason it feels safe, the only reason you woke up this morning to a world you recognized, is because a rock the size of Mars slammed into our planet 4.5 billion years ago and knocked it crooked. That crooked angle became your seasons. Your harvests. Your migrations. Your evolution. You are not a passive observer of the cosmos. You are the cosmos observing itself, a temporary arrangement of atoms that somehow learned to wonder why it exists at all. And now you know part of the answer. The rotisserie keeps turning. The moon keeps watching. And somewhere in the back of your mind, a question is forming that wasn't there 20 minutes ago. Think about it. What other accidents in your life turned out to be essential? What catastrophes became foundations? What collisions, personal, painful, unexpected, knocked you into an angle that made everything else possible? Do you believe Earth's stability is a cosmic fluke, or evidence of something deeper? If we found another rotisserie planet tomorrow, would it change how you see our own? And here's the one that might keep you awake tonight. If the moon drifted away over the next billion years, and Earth began to tumble, would humanity find a way to survive? Or would we become another silent world in a galaxy full of them? These questions don't have easy answers. That's what makes them worth asking. If conversations like this matter to you, if you want to keep exploring the strange, beautiful, terrifying truths hiding in plain sight, stay close. More cosmic journeys are coming. The universe never stops whispering. The only question is whether you're listening.